Hey folks, Bryan here, CEO and co-founder of Wilderness Labs. So I wanted to show you guys a little bit of some details of Meadow. I'm gonna do a video. It's kind of a series of videos showing some various things about it. But today, I wanted to take a few minutes to do a bit of a deep dive into some of the underbelly of Meadow, if you will. So Meadow is an interesting solution, and there's a lot to it. And I think a good place to start to understand it is taking a look at the Meadow stack. So if we look at this image that I have up on my screen now, you can see that Meadow is basically divided into three major components. And at the very bottom is the Meadow operating system. And the Meadow operating system is a heavily modified micro RTOS. In this case, we use NutX, which is an open source, very permissibly licensed micro real-time operating system. And we've modified that to work on our custom hardware, and I'm going to show you what some of that looks like in a moment. But basically, getting a micro operating system like this up and running on a chip isn't terribly difficult. But as you start to add other pieces to it, as you start to add flash and memory and other things, other peripherals and whatnot, it becomes quite a challenge to sort of like get it all configured right and whatnot. And it's all very low level stuff. At the base of Meadow is our real-time OS, which I mentioned is built off of NutX. And then on top of that, we have a heavily modified Mono runtime. So Mono is really fantastic because unlike like .NET Core, CoreFX, it runs on a lot of really interesting architectures. Now, in the case of the Meadow F7 board, we're running it off of an ARM architecture, and of course, Mono running on ARM got very, very good and very optimized in the days of, in the sort of Xamarin heydays, is because it's what powers iOS, it's what powers iPhone and Android, are ARM chips. And so Mono runs very, very well on ARM. So we have modified the Mono runtime so that it lives on our NutX install, and the NutX, our NutX package is very heavily modified for our hardware, and it's not just configuration stuff. It's we have to expose certain hooks so that exceptions, for example, in .NET are handled really well, and are have native support throughout the Mono stack, and we've made a bunch of memory, the way that we handle memory and the way that memory is accessed and whatnot. We've had to make that much more friendly to managed runtime and whatnot. And of course, because we are using Mono, we get the full .NET Standard 2 API surface area. Now, in fact, we actually get a lot more than that. There's a whole set of APIs and whatnot that aren't included in the .NET Standard API, but what it does mean is that any of the NuGet packages that target .NET Standard 2, which now is like the most common standard, those will just run. In addition to that, we have a bunch of other APIs and stuff. That's a good segue. So the second piece of this is Meadow Core. And Meadow Core is a managed library that runs in Mono on top of the Meadow OS. And what we're calling Meadow OS is a heavily customized NutX with the Mono runtime and the rest of our goodies in there to make all that work really well. So Meadow Core is what you can think of as it's kind of like maybe iOS Foundation APIs or Windows APIs, etc. So this is the core API that you would use to talk to Meadow, and I can show you some of this here. If I let me pull up an application here. So this is a Meadow application. that runs on our board, and you can see here what this API looks a little bit like. So when you're creating a Meadow app, you create an app and you inherit from app base, and then you pass your device type. In this case, it's F7 Micro. This is how we support a lot of different. Well, we will support a lot of different devices, and so we've thought about this from an API standpoint from the very beginning. So in this case, you say F7 Micro, and then you pass it the type of your app, and we do this because later on, if you ever want to get access to this anywhere in your application, you can always get to the current instance of your application and its type. So var foo is actually, let's make this goo. Var foo, if you see the type here, then you see that it's typed as RGB app. And so we do some magic behind the scenes with that. And this is all pretty basic. If we look at this app, so there's a constructor, and in this case we're creating an RGB PWM LED. So there's an RGB LED on the board, which is it's a really nice high quality LED, and you can do the sort of colors of the spectrum on it. So we have a class level variable here, and we instantiate that, and then we say new. So onboard LED equals new RGB PWM LED, and there's a couple of ways to instantiate this. So so the first one is to instantiate it with pins, and in this case we say device.pins, and then you have onboard LED red, blue, and green. But you can also instantiate it with ports. So we have this thing called the unified GPIO architecture, and the idea behind this is that when you add things like I/O extenders, GPIO extenders, like shift registers and other I/O extenders like analog, or like mutexes, so where you could you read from different analog ports and expand your analog inputs, and like MCP chips, etc. There's these chips that allow you to basically add more I/O in both digital and analog. And these chips are in everything. They drive LCD screens, they drive screens, they're in a lot of stuff. And so what we've done is we made it so that you can add these chips to your circuit, to your add it to your Meadow, and then you can use them as if they were all of those I/O ports were part of your Meadow app. And so that's what this GPIO architecture allows you to do. I'm not sure actually why this is using Meadow hardware. So you can either pass it as a pin as a shortcut, which is notated on this class, this device class. And actually, if you look at this device class, you see it's an F7 Micro. And so this is really cool, because when we pass this in the very beginning, we specify this is an F7 Micro. Now, whenever we say device, we actually get a strongly typed class that enumerates the various things on that device. So if I do device dot pins, you can see here's analog, here's the digital, and then here's the onboard stuff. So it's a really nice shortcut to get there. But the other way that we can do this is that we can pass in a port. Like in this case, this RGB PWM LED wants a PWM port. And a PWM signal, PWM is a type of digital signal that goes on and off very, very fast. It oscillates, and what that means is instead of having like on or off, 0 or 1, 0 or 3.3 volts, you can actually get an average voltage, and so you can use a PWM signal to emulate an analog output, and it's a good way to regulate the voltage for LEDs, and a lot of different motors require PWM signals for controlling signal. So like servos and step motors, etc. They're controlled by PWMs. And one of the awesome things about this board is that every single digital pin on here is also a PWM. So there's 16 there's a 16-bit digital output here. So there's 16 digital pins, and every single one of them has a timer on their PWM timer. So that's pretty awesome. Anyway, in this case, let's say you had created an MCP chip, which is an I/O expander. Then that would give you these ports, and so you can then create a peripheral like a PWM LED or a relay or something using the pins from, or using the ports from that MCP chip. So it basically makes it seamless to use these I/O expanders. So it simplifies a lot of hardware stuff. And then because we have, so here's some fun stuff to show you. Because we have full .NET, you can see this particular example runs the onboard LED through a series of, through the hue spectrum, or it will. You'll see we're missing something. We haven't converted yet, but because we have full .NET, we have things like async and await, and I'm sure that I'm doing this wrong because it's async and await. but the what's cool here is that I can just as with any other modern .NET app, I can new up a task and I can set it to start, and I can set it off in the background, and even though this is a microcontroller, we have these concepts of modern threading, where we abstract the thread away and we think of things as tasks and whatnot, and that's something that's really, really cool, because you don't get that in really any other platform. And there's some threading and some of the, if you're doing low-level C++ stuff, but like for example, Arduino is single-threaded, so a lot of things are just very difficult, if not impossible, practically impossible to do. So this is really cool to have these modern constructs. And I want to kind of show you folks, how this all sort of shapes up in our development environment as well. But before we get there, let's talk about the next piece of Meadow. So one of the things that makes Meadow really easy to develop for is this Meadow Foundation. And Meadow is really a full stack IoT platforms or development platform. So if you look at Meadow Foundation here, you see peripheral drivers and libraries and sensor drivers. So the idea behind that Meadow Foundation is that when you go out and you buy some peripherals from SparkFun or Adafruit or something, instead of having to go and fight with drivers and search for drivers and find broken drivers and none of the drivers work the same, etc., we've created this open source library of peripheral drivers and hardware APIs. So what's really nice about this is that you plug in your sensors, your LCD screens and your relays and stuff like that, and they just work. We have a really nice API for those things, and they're curated in such a way that they support the GPIO, the unified GPIO architecture, and they all work the same. So there's a lot of like contracts and in interfaces around these various things. The idea here is that no matter what version of a particular peripheral you get, they act the same, so a relay is going to act like a relay no matter what. And to get an idea of what some of that stuff looks like, you can take a look at NetDuino Foundation. In NetDuino Foundation, it's kind of broken up into two different places. It's the core API and the library APIs. In Meadow, it's all in one. It's not broken up like that. But this will give you kind of an idea of what these things, what we support out of the gate, and kind of how those things are put together. And by the way, we plan on open sourcing Meadow Foundation as we get into our early betas. And the idea there is that Meadow Foundation is something that everyone can, the community can contribute to, and we'll curate it and we'll make sure that it's, everything that goes in there is high quality and high value. But you can also just poke in there, and if you are trying to write a drivers for something new, then you can go in there and you can see how we've done drivers for other similar things and whatnot. So I think that's pretty cool. I want to show you next. I want to show you a little bit of the hardware and kind of how we develop today, because it's a really interesting process. It's kind of, there's a lot. We've been working on this for 2 years, and there's, along that journey, we've had to build a lot of specialized tooling and specialized processes to make this stuff work. So let me show you. I got a camera, my fancy iPhone camera here. Let me pull this up. So this is, you can see here, this is the Meadow F7 debug board right there, and here it is up close, and this is the current last revision, I guess I would say. Today we're actually getting new PCBs for the newest revision of this one, and the reason why is that this one has actually a couple of fun mistakes. Let me show you what the result of that is. So here is that debug board fully wired up, and it looks like a patient in a hospital, some sort of like Frankenstein electronic patient. We have, coming off of it, we have a JTAG. So this is a JTAG header, and this is JTAG adapter. So this is USB to JTAG. And then over here we have serial to USB board. And then we have the regular, of course, just plug in. So this is where we get USB power, and this is where we can do some DFU flashing and stuff. I'll tell you about that in a moment. So we made a couple of mistakes on this board. Let me show you the first mistake that we made. This was kind of a fun one. So we got the boards, and I plugged them in and I put them into DFU mode, which bootloader mode, which for those of you who have done Arduino development or other microcontroller development, you're probably familiar with this. You hold down your DFU boot button and then you plug in the USB, and then that puts the chip into this special mode where it's sort of ready to accept a stream of bytes that will be flashed to the chip. So I held down the button and I plugged this in, and the board didn't show up in system information. And system information is where we go to find like all of, it's an easy place to view where all of your USB devices and stuff are. In any case, the board didn't work. And we're checking everything. Power's all perfect. Everything's perfect on the board. We're looking with our oscilloscope and our multimeter, and we're going through this. And it turned out that we hadn't powered the VDDA pin. It was unclear in the data sheet whether or not that actually needed to be powered, and it turns out it does need to be powered, even though we were providing a reference voltage elsewhere. Anyway, I wound up having to solder this little tiny copper jumper between. There's an LED. I think this is the LED, and this is a capacitor, and so you can't tell, but this is hair thin wire. This is in like some really thin like jumper wire, something like this. I opened this up, and there was some there was like a braided wire in there, and I took that one little piece of wire and had to solder that under the microscope, and lo and behold, we did that, and then I plugged the board in, and we had, the board showed up in DFU mode, the board showed up in non-DFU mode, and we saved our prototype. In a note about prototypes, it's a time-consuming process to rev a new prototype. Now, if we had tons of money, if you had the design on Monday, by Friday, I could get in my hands a the actual physical prototype. And that means doing a 1-day turnaround on the PCB boards and then doing like a 2-day turnaround on the assembly of those boards. As it is, because we're a small startup and we're bootstrapped, we have to save money. So we send our design off, and it takes us a week to get the PCB boards back, and then it takes another 2 or 3 weeks to get assembly, and there's time in between there and stuff. So the upshot is that it usually, and then it takes us time to do the testing and stuff. And so the upshot here is that every prototype that we churn costs us about a month. And if you include the design phases, the design phase for design changes and stuff, it can be like a month and a half, or it can be even 2 months. And so had we not been able to jerry rig this board to make this work, then we would have lost another like month and a half to a hardware failure, which is no fun. And so we were really happy long story short, we were really happy when this jumper worked. When I was able to, first of all, soldering this was a nightmare. I literally had to do it under a microscope, but when it worked, it was really awesome. And it took me, I think I destroyed 3 of these trying to perfect that solder. So anyhow, that's the debug board. There's 4 main things to take a look at on this board in terms of like debugging and whatnot, and communication with it. So the first one is we have JTAG, which is where we can, so that's one way we can communicate with the board. And then we have serial debugging, and that one is actually supposed to come out over here. So if you look at this, there's a USB adapter here, and then there's this little chip. And that actually hooks up to serial on the microcontroller. So if you look at this board over here, everything that's on this board is basically in this little section right here. In fact, there's LEDs here, and there's little tiny LEDs here, and here's this FTDI chip which converts serial to USB. And the reason why we have this sort of extra Frankenstein thing here is that we made a mistake. We made 2 mistakes on this board, and this is common, by the way, to prototype hardware and have mistakes. Think of it as like when you're doing software and you write your code and then you find your bugs and then you redeploy. Well, hardware is a little bit different because redeploying means making a new prototype. So anyway, we have this serial to USB interface here, and what this does is that we use this in the process of debugging. So talking to this hardware is kind of a challenge, and so we use kind of every interface we can to help debug. And in this case, it's really easy for the chip or the NetX to output debug information over serial. And ordinarily we'd just plug in a USB, but because we swap, I'm not sure if I mentioned this. The mistake that we made here was that we swapped the RX and the TX lines. So effectively made this section of the board completely useless. So what this thing here does is it basically serves as this section of the board. It converts serial to USB, so I can plug it in and then I can connect to the device via serial. And then you can see here in this window, you can see these are debug information that comes out of the board, and there's a number of different ways we debug this. It's a really kind of a complex setup. If I swap over to my terminals, it feels a little bit like the Matrix here. In any case, so we to debug this thing, I mentioned that the serial USB stuff was one method, but the other thing that we use here is that we have to deploy our applications to the device. And there's 2 ways that we can do that. The first way is that we can put it into a bootloader mode by holding down the boot button, plug the USB in, and then we can shove our package over onto the device's flash. That is a very reliable, very good way to get the Meadow package, which is the operating system and the APIs, and then your app. The other thing that we use sometimes is ST Flash. Now this is got the upside of not needing to put your device into DFU mode. So it basically is listening for this, and then you can send it over and flash it anytime you want. And in this case, if I recall, that goes over JTAG in our setup. I may be confusing that, but I think that's over JTAG. The problem with that is it is not as reliable as DFU, but we do need JTAG to do real-time debugging the OS. And so we use the GNU debugger to do that. And this is really interesting. So basically, when the device is running, and I'm not sure actually what it's doing right now, but we over JTAG we have this debugging session, and we can connect to it, and we can debug in the terminal. So here's this is actually a debugging session. So imagine that this is the terminal version of hitting a breakpoint in Visual Studio or something. So you have things like backtrace. You can see your stack, and you can continue, and you can do things like that. There's some real magic here to make this happen. Basically, what we've done is we've implemented this thing called semi-hosting. And semi-hosting allows you to connect a host computer to the device, and basically it exposes the host computer as if it were a peripheral. And so we can do console.writeLine, and the console.writeLine comes over our semi-hosted ST-Link, and then we can see that. So when we do hello world, we can actually see hello world output over this semi-hosting. The other thing that is nice is that we actually can share the file system locally on the host machine with the device. So if you look over at my Finder here, and we look into my temp directory, so when we launch, when the chip comes up, when the board comes up, we actually, as a way to debug and a way to load things right now, we actually launch our mono apps out of the temp drive on our host computer, which is really interesting, because the way that this works is that Meadow, on this board, Meadow operating system, which is the mono runtime and the OS, is about 1.5 meg. It's about 1.6 megabytes. And we load that up into the SRAM on the chip, which is very, very, very fast. And then we've got two ways we can execute an application today. We can bundle everything up into the OS package, and we can flash it to the chip, and then run it from there. And what we do is that we execute the application from the flash memory on the board, which means instead of like loading it into memory, the flash chip actually acts as memory. And then we have our additional RAM for a heap and whatnot. But that takes a little while, because we have to bundle this whole package up, and we have to flash it and then run it that way. But the other thing that we can do is that we actually can build our mono application. We just drop it in the temp directory, and then we load it from there. So the board boots into Meadow, and then it will go and load the application from the temp directory. And that allows us to deploy apps faster, because we don't have to flash it every time to do that. We just have to reboot the board, and it'll load whatever apps in there. We have a whole lot of work to do around the development tooling and whatnot. But for the upshot for you is that what will happen is that you'll write your application in Visual Studio or Visual Studio Code as it is, as we saw it over here. And then you'll be able to hit the button here. You hit, we'll have the drop down up here. We'll say, device. You hit this button, and it will deploy to it'll compile your application, and then it will deploy it over USB to the OS that's sitting there and waiting for it. So then you'll be able to do, you know, rapid deployments and testing and whatnot. And the great thing about this is because it's all mono and it supports mono debug stuff, you'll be able to hit, you know, breakpoints and step through the application and whatnot that way. Today, you know, it's a little bit more primitive than that, but you know, when we do get this into beta for you, when we get to, you know, the private beta, you'll see that this will have a much better flow. So anyhow, that was I know that was a very deep sort of technical dive into some of this stuff, but there have been a lot of questions from folks who are deeply technical that wanted to know how a lot of this stuff works, and so I thought I would take a moment to kind of jump in through some of this and also show you some of the crazy stuff that we're having to do so that you don't have to. So stay tuned. I'm going to do some more of these. I think that, you know, the next one we'll actually walk through doing some applications and whatnot and show you some more of it. So also let me know if there's anything that you want to see in these. If there's anything that you want me to talk about, you know, let us know. So anyhow, thank you for listening and watching.